All right, if you're anything like me, you've probably faced that challenge, right? Needing to really get your head around a complex topic fast.
Yeah, quickly, but without, skimming over the important stuff.
Exactly. You don't want to sacrifice depth. The internet just throws mountains of info at us. How do we find the really crucial insights and find them quickly?
It's a constant battle.
Well, today we're diving into something pretty fascinating from Google. It's called MUVERA.
MUVA, yeah. Stands for Multi-Vector Retrieval via Fixed Dimensional Encodings. Bit of a mouthful.
Definitely. But the key thing is, this isn't just some, minor tweak to search results.
No, not at all.
It's actually a pretty sophisticated algorithm, and it's designed to boost both the precision and the efficiency of search.
The promise is more accurate results that really fit the context of what you're asking, better than ever before.
What's really exciting, I think, is how MUVERA basically offers a shortcut.
A shortcut to being genuinely well-informed, yeah. It works by figuring out the deeper meaning, the context behind complex questions.
Using multiple vectors, multiple dimensions to understand what you really mean.
Exactly. It's about combining that richness, that deep understanding, with the speed we all, frankly, need.
So, our mission today, if you will, we want to unpack how MUVERA pulls off this balancing act.
Look at the clever engineering behind it.
Yeah, explore the engineering and figure out what it all means for how you find information day to day.
That was good.
Okay, let's get into it.
Let's do it.
So, to really get why MUVERA is a big deal, we kind of need to step back first. Understand the basic challenge in search today. Why is it so darn hard to be super fast and super precise at the same time? It often feels like, you have to pick one.
It really does. And if you zoom out a bit, traditional search, the single vector kind, it's a bit like summarizing a whole movie in just one sentence.
Okay, I get the main plot point.
Right, you get the gist, and it's really fast to compare that summary with others. But you miss, well, everything else. All the nuance, the plot twists, the characters.
Yeah.
These older systems, they compress all the meaning of a document into one single vector. One point in space, basically.
Which makes searching fast. You mentioned MIPS.
Exactly. Maximum minute product search, or a MIPS. That's the standard way to compare these single vectors quickly. But the cost, often, is that precision. You lose too much detail in the compression.
Okay, so that's one side, speed, but maybe lunk detail. What about the other way? Getting that precision, that richer understanding, like watching the whole movie?
Well, that's where multi-vector models come in. Things like Colbert, for example.
Colbert, right?
They're designed very differently. They aim to capture much richer relationships between words and ideas.
How do they do that?
Instead of one vector for the whole document, they represent each token, basically. Each word, or even part of a word, with its own vector.
Okay, so lots more vectors per document.
Loads more. And when you search, different parts of your query, different query tokens can match different parts of the document. Different document tokens. It uses a different comparison method, too. Something called chamfer similarity, or sometimes maxim.
Chamfer similarity. How does that work?
The key idea is, instead of one overall comparison, chamfer lets each individual word, each token in your query, sort of hunt for its best possible match among all the tokens in the document.
Okay. So learning, in my query, finds the best match for learning in the document. Healthcare finds its best match.
Precisely. And then it combines those best individual matches to get a final relevance score. It's much better at capturing subtle meanings because it's not forcing everything into one average representation.
That sounds incredibly powerful. Like you're really comparing the detailed script of the movie, not just the one-sentence summary.
It is powerful, yeah.
But there's always a but, isn't there? What's the catch? This sounds computationally heavy.
That is exactly the catch. Computational expense. And it's a huge one.
Okay.
Comparing these sets of vectors, token by token, is just agonizingly slow.
Give me a sense of scale.
Okay, imagine your query has, say, 32 tokens, 32 words, or word parts. And a document you're comparing it to has maybe 80 tokens.
Right.
Just comparing that one query to that one document involves 32 times 80. That's 2,560 dot product calculations.
2,500 calculations for one document.
For one document. Now imagine your search index, your corpus, has maybe 8 million documents.
Oh.
You're doing 2,560 times 8 million. That's over 20 billion operations.
To 20 billion per query.
Per query.
Wow. Okay, my brain hurts just thinking about that number. It's like, trying to track every raindrop in a storm manually.
Exactly. It's completely unfeasible for real-time stuff.
You couldn't run a search engine like that. People expect instant results.
Absolutely not. It becomes prohibitively expensive. You need massive amounts of storage for all those vectors, and the latency, the time it takes to get an answer, is just way too high. Impractical.
I definitely see the dilemma now. Speed versus precision. So what if people tried existing solutions? Have they managed to crack this?
Well, people have definitely tried. Systems like PLAID, for instance. They try to get the best of both worlds.
PLAID, how does that work?
They use these really complex multi-stage pipelines, lots of steps.
Oh, okay.
Essentially, they might do a quick initial search, maybe with single vectors, to get a rough list of candidates.
Okay.
Then they apply more complex steps, maybe retrieving full embeddings, then doing some filtering, then maybe a final re-ranking.
Sounds complicated. Like lots of moving parts.
It is. It works to a degree. But it's like trying to have one smooth conversation by making, I don't know, a dozen short, choppy phone calls back and forth.
Good analogy.
The sacrifice is simplicity. And tunability becomes a nightmare because you have so many different stages and parameters you need to tweak and balance.
Okay, so that sets the stage perfectly. If the existing ways are so complex, how does MUVERA approach this? What's its big idea to bridge that gap between precision and speed without all that complexity?
Right. This is where MUVERA gets really interesting. The core insight, the shift in thinking, is that the problem isn't necessarily the multi-vector representations themselves. They give us that richness we want.
Okay.
The real bottleneck is that we just haven't had efficient ways to search over them directly.
Right, the 20 billion operations problem.
Exactly. So MUVERA flips the script.
Yeah.
Instead of trying to do that complex token-by-token search directly or building those messy pipelines, it creates something new. It creates what's called a Fixed Dimensional Encoding, an FDE, for each document and each query.
A Fixed Dimensional Encoding, FDE. Okay, what is that exactly? What's encoded in there?
Think of an FDE as like a very smart, highly optimized fingerprint, or maybe a structured summary.
Okay, a fingerprint.
Yeah, and it's asymmetric, which is important. We'll get to that. But it captures the essential characteristics, the important semantic features of all the individual token embeddings in the original query or document.
But it captures them in a compressed form.
In a very compact single vector form. And here's the crucial property. When you calculate the dot product between the query's FDE fingerprint and the document's FDE fingerprint.
A single dot product, like in the fast MIPS search.
Exactly. Just one standard dot product. But the score you get from that single calculation very closely approximates the score you would have gotten if you'd done the full, super expensive chamfer similarity calculation between all the original token vectors.
Whoa. Okay. That does sound powerful. Almost like magic. It reduces that complex multi-vector comparison down to a single vector comparison.
That's precisely it. It's a transformation.
But my immediate question is, how? If you're compressing all that rich detail into one fixed vector, aren't you bound to lose something? How does it keep the fidelity?
That's the cleverness of the FDE construction. The transformation is designed specifically to preserve the information needed for that chamfer similarity approximation.
Okay.
And the huge advantage is because the end result is just a standard single vector, you can plug it into any existing maximum inner product search, MIPS algorithm.
So all the fast search infrastructure that's already built.
Exactly. All the highly optimized graph-based search methods, all the indexing techniques developed over decades, you can just reuse them. No need to reinvent the wheel for the search part.
That's a massive practical advantage.
Huge. And critically, MUVERA's approach comes with theoretical guarantees. You can actually prove bounds on how well the FDE dot product approximates the true chamfer similarity. Meaning you can tune the system, adjust how the FDEs are built to get the specific accuracy versus speed trade-off you need for your application, and you have mathematical confidence you're not throwing away relevance.
Okay, that's impressive. So how does the actual search process work then? If you have these FDEs, is it still multiple steps like PLAID?
No, it's much simpler. MUVERA basically operates in just two straightforward stages, way simpler than PLAID's 4 or more.
2 stages, what are they?
Stage 1, you use the FDEs, you take your query FDE, and use a standard fast VIM-B search over all the document FDEs in your index.
Okay, the fast approximate search.
Right. This gives you a list of candidate documents, maybe the top few hundred or thousand that look promising based on the FDE approximation. It dramatically narrows down the field.
Got it. Then stage 2.
Stage 2.
Yeah.
You take just those candidates, that much smaller set, and now you apply the exact expensive chamfer similarity calculation using the original full token embeddings.
Ah, so you only pay the high computational costs for a small number of top candidates.
You re-rank just the best potential matches using the perfect scoring function. This ensures you get high accuracy in the final results you show the user.
That sounds elegantly simple compared to the multi-stage pipelines.
It really is. Dramatically simpler. Fewer parameters to tune, fewer potential points where things can go wrong. It's more robust, easier to manage, easier to understand.
Okay, we've seen the what and the why, this amazing balance of precision and speed, but I really want to understand the magic now. Let's lift the hood on those fixed dimensional encodings. How does MUVERA actually build these smart summaries? How do you take all those individual token vectors and squash them into one FDE that still holds the key information?
Yeah, this is where the really clever engineering comes in. The breakthrough realization was that you don't actually need to perfectly preserve every single tiny detail of how every query token interacts with every document token.
Okay.
You just need to preserve the similarity relationships that actually matter for ranking, for retrieval quality.
Like you don't need every word of the book, just good chapter summaries to compare.
That's a great analogy. If the chapter summaries are structured well, you can tell if two books are similar without reading every single word. The FDE is like that structured summary.
So how does it start? How do you group things? You mentioned simhash before.
Yes, the first step is partitioning the embedding space, grouping similar token embeddings together. And MUVERA uses a technique called simhash, which is based on locality-sensitive hashing.
Simhash, okay, break that down. Forget hyperplanes for a sec. How does it sort these embeddings? Like sorting books in a library.
Exactly like that, but in a high-dimensional space. Think of it as a super-fast classification system. For every single token embedding the digital representation of a word, simhash basically asks a series of simple yes-no questions.
Questions like what?
Each question is defined by a random boundary, technically a hyperplane, cutting through the embedding space. Does this embedding fall on side A or side B of this boundary?
Okay.
If it's on one side, maybe it gets a 1. If it's on the other, it gets a 0. You do this with a few different random boundaries.
And string the answers together.
Yep. You string together the ones and O's, maybe you get 1, 1, 10. That binary code becomes the region ID for that token embedding, like a shelf number in your library.
And the magic is?
The magic, the locality-sensitive part, is that embeddings which are close together in the original high-dimensional space, meaning they represent similar concepts, are very likely to fall on the same side of most of those random boundaries.
So similar words end up with the same or very similar binary codes. They land in the same region.
Exactly. They get assigned the same region ID.
So our library now has books grouped by subject, and each book has a specific shelf number based on these rapid simhash classifications.
Precisely. Now, you might ask, why use random boundaries, random hyperplanes? Why not try to learn the best ones?
Yeah, that was my next question. Random seems, well, random.
It sounds counterintuitive, but random hyperplanes have some big advantages here. First, they're data oblivious. Meaning they work reasonably well for any data set without needing complex data-specific training beforehand. This makes this system much more robust if your data changes or shifts over time.
Okay, robustness.
They're also simple to generate and implement, and the whole process is well-grounded in theory. Plus, you can easily control the granularity, how many regions you create, just by changing the number of random hyperplanes you use.
How many typically?
Usually just a handful, maybe 3 to 6 hyperplanes. If you use, say, 6 hyperplanes, that gives you 2 to the power of 6, which is 64 distinct regions. That often provides a good balance between grouping similar things and keeping the number of groups manageable.
Okay, so simhash uses these random boundaries to assign every single token embedding from both queries and documents into one of these, say, 64 regions. Right. What's the next step to get the FDE?
Right. Now comes the really crucial part, the aggregation step, and specifically asymmetric aggregation. This is the real heart of the FDE.
Asymmetric, meaning you treat queries and documents differently.
Exactly. MUVERA uses different strategies for combining the token embeddings within a region, depending on whether it's building a query FDE or a document FDE. And this difference is designed to mimic how the full chamfer similarity works.
Okay, how does it differ?
For query FDEs, for a given region, you take all the query token embeddings that landed in that region, and you simply sum them together.
Just add them up.
Add them up. Vector addition. This ensures that every token in your query contributes its full weight or importance to the final score. You want every part of your question to count.
Makes sense. And for documents?
For document FDEs, it's different. For a given region, you take all the document token embeddings that landed there and you average them.
Average instead of sum? Why?
This prevents a single common word in the document, if it appears many times and lands in the same region, from completely dominating the score for that region. Averaging ensures you're capturing the general meaning of the document's tokens in that region, aiming for the best available match for a query token rather than just being overwhelmed by frequency.
Okay, summing for queries, averaging for documents, that's the asymmetry. Can you walk through an example, make it concrete?
Absolutely. Let's use your earlier query, machine learning healthcare applications.
Okay.
And maybe we're comparing it against a document titled AI algorithms for medical diagnosis and patient care.
Got it.
So after SimHash runs, let's imagine machine and learning from the query both land in, say, region 3, healthcare. Query lands in region 7. Applications query maybe lands in region 5.
Right.
Now for the document. AI and algorithms might also land in region 3. Medical and diagnosis might land in region 7. Patient and care maybe in region 8.
Okay, map to regions.
Now we build the FDEs. For the query FDE, the part corresponding to region 3 will be the sum of the machine embedding vector plus the learning embedding vector. The part for region 7 is just the healthcare embedding. Region 5 is the applications embedding.
Okay, query FDE built by summing within regions.
For the document FDE, the part for region 3 will be the average of the AI embedding and the algorithms embedding. The part for region 7 is the average of medical and diagnosis. Region 8 is the average of patient and care. And importantly, region 5 is empty for the document in this example.
Ah, what happens then? If the query has applications in region 5, but the document has nothing there?
Good question. This is handled cleverly. For the document FDE, MUVERA has a strategy often called fill empty clusters. If a document region is empty, it doesn't just leave it as 0. It might fill it with, say, the closest non-empty region's average vector from that same document.
Ah, so the query token still has something relevant from the document to compare against, even if not a perfect match in that specific region.
Exactly. It prevents query terms from getting an unfair 0 score. Just because the document didn't happen to have a word fall into that exact arbitrary SimHash bucket, it makes the whole approximation much more robust.
That's smart. So when you finally compute the dot product between the query FDE and the document FDE,
the contribution from region 3 in that final score comes from comparing machine plus learning against average AI algorithms. The contribution from region 7 compares healthcare against average medical diagnosis, and so on for all regions.
And that single dot product calculation across all these aggregated regions gives you a score that's very close to the full slow chamfer score.
That's the core idea. It approximates it very effectively, but in a single fast vector operation.
Okay, that makes the process much clearer. Now, you mentioned tuning. How do we manage the size and quality of these FDEs? Are there knobs we can turn?
Yes, absolutely. There are 2 main tuning knobs you can use to control the trade-off between the FDE's size, the resulting search speed, and how accurate the approximation is.
What's the first one?
The first is called inner projections. Before you even do the aggregation, summing or averaging, you can take each individual token embedding vector and reduce its dimensionality.
Shrink the building blocks.
Exactly. Maybe your original token embeddings are, say, 128 dimensions. You could project them down to maybe 32 or even 16 dimensions first. This makes the final aggregated vectors in the FDE much smaller and faster to compare.
But presumably, projecting down loses some information.
It does, yes.
Ah.
So there's a trade-off there between compactness and fidelity. That's one knob you tune.
Okay. What's the second knob?
The second is multiple repetitions. Remember how SimHash uses random hyperplanes? Well, one set of random hyperplanes might, just by bad luck, group things poorly for a specific query document pair.
Right.
To make the system more robust against that randomness, you repeat the entire process, generate new random hyperplanes, partition all tokens, aggregate asymmetrically multiple times, maybe 10 or 20 times.
So you create multiple independent FDEs for each document and query.
Sort of. You create multiple sets of aggregated vectors, one set from each repetition, each using different random hyperplanes. Then you simply concatenate all of these together to form the final, larger FDE.
Ah, so if one repetition was unlucky, the others will likely compensate.
Precisely. It averages out the randomness and significantly improves the robustness and accuracy of the approximation.
So the final FDE dimension depends on the number of regions, the projected dimension, and the number of repetitions.
Correct. For example, if you have 64 regions from 6 hyperplanes, project down to 16 dimensions internally, and use 10 repetitions. Your final FDE dimension would be 64, 1610 equals 10,240 dimensions.
10,000 dimensions. Still sounds large, but I guess compared to dealing with potentially hundreds of original token vectors per document and billions of comparisons.
It's vastly more efficient to search over a single 10,000 dimensional vector using optimized MIS algorithms than to do the full token-by-token chamfer comparison.
Okay, this makes sense. We've gone deep into the mechanics, the how, but now let's talk results. What does this elegant engineering actually mean for performance in the real world?
Right.
Is this just, theoretically nice, or does it actually deliver tangible speedups and maintain accuracy when you put it to the test?
That's the crucial question, isn't it? Theory is great, but does it work in practice? To find out, we really needed to benchmark it, put it head-to-head against the best existing methods.
So who did you compare it against?
We compared MUVERA directly against PLAID. As we discussed, PLAID represents the state-of-the-art for trying to do efficient multi-vector retrieval using those complex multi-stage pipelines. It's highly optimized.
Okay, the heavyweight champion. And what was the testing ground?
We used a pretty challenging and realistic data set called SciDocs.
SciDocs.
Yeah, it's made up of scientific papers, abstracts, and titles, and complex queries related to those papers. It simulates the kind of difficult information retrieval task you'd find in, say, a research search engine or academic discovery tool. High stakes, complex language.
Perfect. So a proper head-to-head, complex, established PLAID versus elegant, two-stage MUVERA in a tough environment. What happened? What did the numbers show?
The results were pretty striking, honestly.
Okay.
First, the PLAID baseline. It did well on accuracy, as expected. It achieved a recall at 100 of 0.98.
Meaning it found 98% of the truly relevant documents within the top 100 results it returned.
Exactly. Very high recall. But that complex pipeline came at a cost. The average latency, the time per query, was 92.12 milliseconds.
Okay, 92 milliseconds, just under a tenth of a second. Fast, but maybe not instant feeling.
Right. Now, enter MUVERA. We tested two things. First, what if you only use the FDE search? Just stage one, the fast approximation, with no re-ranking stage afterwards.
Okay, just the raw FDE speed.
The latency dropped dramatically, down to just 0.4461 milliseconds.
0.4 milliseconds compared to 92.
Yep, that's a 206.5 times speed up.
Wow. Okay, that's enormous. 200 times faster.
It really highlights just how efficient replacing the whole multi-stage dance with a single smart FDE transformation in MIP search is.
But what about accuracy? Just using the FDE approximation must lose some recall compared to PLAID.
It does lose a bit, yes. The recall at 100 for FDE only was slightly lower, but then we tested the full MUVERA pipeline. Stage 1 FDE search followed by Stage 2 chamfer re-ranking of just the top candidates retrieved by the FDEs.
Okay, the full two-stage MUVERA, what was the latency then?
The total latency for the full MUVERA pipeline was just 5.048 milliseconds.
5 milliseconds, still way, way faster than PLAID's 92 milliseconds.
Massively faster. It's still an 18.2 times speed up over the state-of-the-art PLAID baseline.
An 18-fold speed up. That's incredible. For us using search, that's the difference between something feeling fast and something feeling truly instantaneous, like results appearing as you type.
It enables user experiences like predictive search, live recommendations, things that were just computationally borderline before. It makes them practical. Okay,
but here's the absolute crucial question. We got this massive 18x speed up and incredible simplicity gain. What did we give up in accuracy? What was the recall at 100 for the full MUVERA pipeline?
That's the kicker. Almost nothing. The final MUVERA pipeline's recall at 100 was 0.979.
And 0.979 compared to PLAID's 0.98.
Exactly. It was statistically indistinguishable. Effectively the same accuracy.
Wow. Okay. So let me get this straight. MUVERA matches the accuracy of the much more complex state-of-the-art system, while being roughly 18 times faster and architecturally far simpler with just 2 stages instead of 4 or more.
That's the core takeaway. That's why it's exciting. You get the precision of multi-vector matching, but with speeds approaching single-vector search and without the pipeline complexity.
Simplicity really crushes complexity here, but just playing devil's advocate, for someone thinking about implementing this, are there hidden difficulties? Even with the elegant concept, what's the steepest part of the learning curve?
That's a fair point. While the concept is simpler than PLAID, you still need a solid grasp of vector embeddings, MIP-piece algorithms, and retrieval systems in general.
Sure.
The main work probably lies in properly tuning those knobs we talked about, the inner projection dimension, the number of synhash hyperplanes, the number of repetitions, finding the optimal settings for your specific data and latency budget requires some experimentation.
Right, the tuning.
But critically, tuning those few parameters within MUVERA's 2 stages is arguably much more manageable than debugging and optimizing a complex 4+ stage pipeline where performance bottlenecks could be hiding anywhere.
Makes sense. A more constrained optimization problem.
Exactly. And MUVERA has that other advantage we touched on, being data oblivious because of the random hyperplane.
Right, the robustness is...
Yeah, it doesn't require dataset-specific training for the core hashing mechanism. This makes it much more resilient if your data distribution changes over time, or if you need to apply it to new domains quickly. It's also great for streaming data scenarios, where new documents are constantly arriving and need to be indexed immediately without retraining.
That adaptability is huge in the real world. Things are always changing.
Always.
So let's bring this home. If our goal, as you said at the start, is to be truly well-informed, quickly and thoroughly, what does MUVERA really mean for us, the people actually searching for information?
I think it means search systems can get much better at understanding the nuance in our questions, especially complex ones. It allows the power of those detailed multi-vector models, which really capture semantic meaning well, to be used in production systems where speed is absolutely critical.
So less time sifting through kind of relevant results.
Hopefully, yes. More precise, contextually rich answers, delivered almost instantly. It closes that gap between wanting deep understanding and needing immediate results. Imagine asking a complex question and getting sources that truly address the different facets of it right away.
That sounds like a much less frustrating way to learn and explore.
Definitely. From a systems perspective, MUVERA offers this practical, efficient way to unlock the power of semantic matching that we knew was possible with models like Colbert, but was just too slow before. FDEs provide that bridge.
And beyond just the raw performance, that simplicity factor you highlighted seems key.
It really is. Systems that are easier to build, tune, and maintain are more likely to be deployed widely. MUVERA lowers the barrier to entry for using sophisticated semantic search. It's a compelling technique for anyone building search or recommendation systems today.
So as you, our listeners, navigate that endless sea of information online, maybe pause for a second and consider the tech working behind the scenes. Breakthroughs like MUVERA are quietly, but significantly, reshaping your ability to find what you really need when you need it, to get truly relevant answers instantly.
It's a fantastic reminder that deep, nuanced understanding doesn't necessarily have to come at the cost of speed. Sometimes, elegant engineering finds a way to give you both.
A powerful thought. Finding that balance is key.